Welcome back, National 5, for another installment of Mr. Bull's Physics. This is part 2 of our heat series, and this is specific latent heat this week. Now, I want to talk to you very briefly about the 5 new subscribers that subscribe to the channel. We want to welcome you to the family of Mr. Bull's Physics. But we've got 14 more subscribers until we get to 100 subscribers. I think we can reach that by the September weekend. So if you're watching and you've not subscribed to anything in your life, this could be your first subscription. So I'm going to ask you, subscribe to Mr. Bull's Physics. Right, today we're going to talk about latent heat, and specifically the heat energy involved in latent heat. Now, last week we talked about the heat energy EH equals Cm delta T, and this was only based on the fact of something changing its temperature. So what is the heat energy in changing the temperature of something? Now, today we're going to move on from that and not talk about the change in temperature, but actually the change in state. And a change of state occurs when something goes from a solid to liquid, liquid to solid, or liquid to gas, gas to liquid. Okay? Now, in this change of state, there's actually no change in temperature. The energy is being gained or lost by just changing the state, changing the chemical composition of the material, not in changing the temperature. Now, this graph I'm going to show you will help explain that a little bit. Now, this graph is a graph of temperature against time. And you can see that there's these flat sections. Now, these flat sections are asked again and again in multiple choice questions in the National 5 exam. And we'll see that as you start here, this should be some sort of solid, okay, and this is water, so this will be some sort of solid. It could be ice. And as the temperature increases, okay, the ice gets warmer, and then you reach 0. Now 0 is obviously the melting and freezing point of water. But as the ice is changing state into water or liquid, we can see that the temperature does not change, it stays constant. And then as we hit the point where all of the water or all of the ice is melted into water, only then does it start to raise its temperature, and raises its temperature. And we get to obviously boiling point in this example if it's water, and all the water is now starting to change state into gas or into steam. But it only starts rising temperature once it's all gone into steam or gas. Now that's probably not theoretical what happens, but in National 5 that's all we need to know. And then from the moment it's all gas, it starts to raise its temperature again. Now this is a key graph. Please know it. It comes up again and again in multiple choice exams. Now, this is the equation. The equation is EH equals mL. Heat energy equals the mass times this thing called latent heat. And latent heat is the heat energy required to change the state of 1 kilogram of material. Okay. Now, latent heat is again found in our data booklet, just like specific heat capacity. This is found in our data booklet, and we have 2 different types of latent heat. Okay, one for changing state between a solid and liquid, and one changing state between like a liquid and gas. Now, they have 2 different names. The first name is fusion. Fusion is the latent heat of fusion, and it is the number or the heat energy required to change the state of 1 kilogram of material, and it's going from solid to liquid, liquid to solid. So latent heat of fusion is in your data booklet. For anything that comes up as a question that's asking you about solid melting or a liquid freezing, you're going to look at this latent heat of fusion. But if it's gas, think of vapor, okay? Gas, liquid, liquid, gas. You're going to be doing latent heat of vaporization, okay? Latent heat of vaporization. So whatever question asks, you have to then look accordingly to the data booklet and find out what one you're using. Now, real life example, talking about a shower. Why is it when you go out of a shower or come out of a shower you feel really cold? Why is it you feel really cold? Well, it's actually to do with specific latent heat of vaporization. And the droplets on your body are taking the heat energy from your skin, from your body, and that is then causing them to go from a liquid to a gas. Okay, so there, if you were to leave yourself for 30 minutes without drying yourself, you would eventually just dry off. And that's because of latent heat of vaporization. The heat energy drawn from your body, making you cold, goes into the liquid, and then that evaporates off. Okay, so it's not me, this is science. Okay, this is science. Now, We're going to do some examples, okay? We're going to do some examples. Now, in these examples, first one's going to be nice and straightforward, the second one's going to be a little more complicated. The second one is a typical exam question. So the first one, and I've got my trusty answers here. So the first one here, okay, we're going to write this down. So it's asking how much energy is required to melt 0.25 kilograms of ice. Now, we know it's melting, which means it's EH equals ml. There's no change in temperature here. EH equals ml. The mass is 0.25. And the latent heat, and what are we going to use? Well, it's melting, so therefore it's a solid liquid, which means I'm going to be using fusion. Okay? Times 3.34 times 10 to the power of 5 gives us, and the answer should be 8.35 times 10 to the power of 4 joules. Alright? Easy equation. You can get that. That's fine. Okay? Hardest part is knowing whether or not to use fusion or vaporization. Okay? And I put my answer into scientific notation. Now, this one's more important, and I feel this one's more tricky. Okay? Because what we're going to do is, first of all, we're going to find out the specific heat capacity or heat energy for a change in temperature. Then we're going to find the heat energy for a change of state. Then we're going to add those energies together to answer 3. Calculate the time taken to cool and freeze the ice cream. So, we're talking about a chef puts 0.8 kilograms of liquid ice cream at a temperature 20 degrees Celsius into a refrigeration unit that removes heat at 140 joules per second. Do not get caught out with joules per second. That is simply just watt. What? Watts. What? Watts. Okay? Which is just a power. Okay? So do not get mistaken about that. Now, first question. Calculate how much energy is removed to chill the ice cream to its freezing point of minus 16 degrees Celsius. So, how do we do that? Okay? So we're going to just do one like that. We're going to do EH equals Cm delta T, because we know it's a change in temperature. We knew that was 2100. It's 0.8. And the temperature change was 36, because it went from 20 degrees to minus 16. If I do that in my calculator, I get 6.05 times 10 to the power of 4 joules. Okay? That's number 1. And number 2 says calculate the amount of heat energy removed to freeze the ice cream. So latent heat of fusion again is going to be used, and we've got that down at the bottom. Okay? And that's just going to be EH equals ml. So what I'm saying here is that the equation shouldn't be that difficult, and you should be able to distinguish between what equation you need to use. So 0.8 times 2.34 times 10 to the 5. And we get an answer of 1.87 times 10 to the power of 5 joules. Right, easy. That was quite fast. Pause it, go back if you need to. For the last question, calculate the time taken to cool and freeze. So we need to add the energies, because one was cooling, one was freezing. So we're going to have the E total is just going to be adding these two. So for time, I'm just going to add what those two are, and it's 2.447 times 10 to the power of 5 joules. Now, not rounding it yet because I need to use the answer in the next equation. And the next one would be time equals E over P. That's just that equation, that power equation that we're using. Okay? We know that the total energy is now 2.447 times 10 to the power of 5 divided by 140, because we know that's how many watts, joules per second. And we get answer of 1,770 seconds. Right, you go over that again. Rewind it, look at that again, because that there is a typical exam question. Okay, so I'm helping you out here with this. So have a look over it again. Now, I'm just going to move on, because we're going to finish now. This is the last thing I want to leave up on the board. Okay? And we just see that if you come across a question regarding heat, follow this flow chart. Is it changing temperature? Okay, no or yes? Okay, well then that depends what equation you use. If it's changing state, you use EH equals ml and follow this one. If it's changing temperature, you use EH equals Cm delta T and you follow this one. Okay, so have a look at this and see if it makes sense. National 5, that is the heat, latent heat and specific heat capacity over the last 2 weeks. I hope you've learned a lot from this, and yeah, I hope we have a good week, and we'll stop in again for space next week. Thank you very much, National 5.